Astronomers have spotted something no one expected to find this soon after the dawn of time. In a patch of sky so distant it stretches the imagination, the James Webb Space Telescope has uncovered a galaxy unlike any other. Its name is Infinity, and hidden within it lies one of the most perplexing and awe-inspiring discoveries in modern astronomy: what appears to be a black hole forming not from the death of stars, but directly from collapsing matter itself. This breakthrough challenges everything we thought we knew about black hole formation. Until now, scientists believed that black holes grew slowly over billions of years, forming from the remnants of massive stars. But what Webb has revealed tells a different story, one that starts not with death, but with a kind of cosmic birth we've never directly witnessed before. What makes this even more extraordinary is the age of the galaxy. It existed just a few 100 million years after the Big Bang, meaning it was among the very first structures in the universe. And yet, it already contains a black hole that seems far too large and too developed for its time. This is the mystery of the Infinity Galaxy. And solving it might rewrite the entire timeline of the cosmos. What makes the Infinity Galaxy so special? The Infinity Galaxy isn't just another distant cluster of stars, it's a cosmic time capsule from the very earliest chapter of the universe. Located over 13 billion light-years away, its light has taken nearly the entire age of the universe to reach us. This makes it one of the oldest galaxies ever observed, dating back to a time when the universe was less than 5% of its current age. It was the James Webb Space Telescope that made this discovery possible. Using its powerful infrared capabilities, Webb was able to peer through cosmic dust and see further back in time than any telescope before it. What it saw in the region now known as the Infinity Galaxy was a surprisingly luminous, compact galaxy, glowing brightly despite its extreme age. What made Infinity truly stand out wasn't just its light, but what that light suggested. Inside this ancient system, scientists detected signs of intense gravitational activity and energy patterns that hinted at the presence of a growing black hole. But not just any black hole. This one was already massive, despite the galaxy's youth. Astronomers gave it the nickname Infinity, not only because of its distance and age but because of what it might represent, a doorway to understanding the infinite complexity of how the universe evolved. Unlike typical early galaxies, Infinity showed no sign of star formation remnants that would suggest a traditional black hole growing from supernova debris. Instead, it seemed to host something even more mysterious. Infinity was discovered as part of Webb's Deep Field Survey, designed to study the formation of the earliest galaxies and structures. But what it revealed was far more than expected. It was a snapshot of cosmic history frozen in time, capturing a galaxy that appeared to break all the rules. The Infinity Galaxy challenges assumptions about how early galaxies should behave. It doesn't just emit light, it emits questions. How did it grow so fast? What forces shaped it? And most of all, how could a black hole that size exist so early in the life of the universe? These are the questions that now haunt astronomers. And the answers may lie in a theory that's long been debated but never directly observed, until now. The black hole that shouldn't exist. The black hole at the center of the infinity galaxy doesn't play by the rules. According to our current understanding, black holes form when massive stars run out of fuel and collapse under their own gravity. These stellar mass black holes can then grow over billions of years, feeding on gas, stars, and merging with other black holes. Eventually, they may become supermassive, anchoring galaxies like our own Milky Way. But this black hole, found inside a galaxy just 500 million years after the Big Bang, is already too big. There simply hasn't been enough time for it to have formed through the slow process of star death and accretion. This is what scientists are now calling the black hole paradox. If black holes need time to grow, how can one this massive exist in such a young galaxy? That question has shaken the foundation of cosmic evolution theories. It suggests that something else, something faster and far more powerful, must have created it. One proposed solution is the direct collapse black hole. Unlike traditional black holes that begin as stars, these cosmic giants may form directly from enormous clouds of primordial gas collapsing under their own weight. No supernova. No intermediate star. Just a direct, rapid implosion that skips the usual steps entirely. This idea has been circulating in theoretical astrophysics for years, but the evidence has always been circumstantial. Until now. The infinity galaxy may be the first solid observational proof that direct collapse black holes actually exist. What makes this even more compelling is that Webb isn't just finding one anomaly. It's spotting several ancient galaxies with similar signs, overly massive black holes existing far earlier than they should. That suggests this might not be a rare event, but a common process in the early universe. These findings raise deeper questions. Could direct collapse black holes be the true seeds of supermassive black holes? Were they the engines that shaped the earliest galaxies? And if so, how much of the universe's early history have we misunderstood? What we're seeing now is more than just a black hole that formed too early. It's a cosmic contradiction that forces us to rethink everything we thought we knew about the birth of structure in the universe. The mystery of direct collapse black holes. Imagine a black hole forming not from the fiery death of a star, but from the silent collapse of an enormous cloud of gas. No explosion. No flash. Just gravity pulling matter inward until even light cannot escape. That's the essence of a direct collapse black hole, or DCBH, a phenomenon that scientists have long suspected, but never directly observed. Until now. A direct collapse black hole forms when a pristine cloud of hydrogen gas, untouched by star formation, begins to collapse under its own gravity. This cloud must be massive, millions of times the mass of our Sun, and it must cool slowly enough that it doesn't fragment into stars. If conditions are just right, the entire cloud collapses all at once, bypassing the traditional life cycle of stars and jumping straight to black hole status. This theory solves one of the biggest mysteries in astronomy: how supermassive black holes appeared so quickly after the Big Bang. Traditional black holes need time, lots of it. They start small and grow over billions of years. But if DCBHs exist, they provide a shortcut. They begin life already enormous, capable of shaping galaxies from the very start. The physics behind these objects is complex and delicate. Cooling must be suppressed, which usually means the presence of nearby ultraviolet radiation that prevents the gas from breaking apart. Dark matter halos, vast, invisible structures, play a crucial role, providing the gravitational scaffolding needed for collapse. These halos may guide the gas inward without triggering premature star formation. It's a fragile balance, but one that the early universe may have favored more often than we thought. The James Webb Space Telescope has been instrumental in giving this theory observational weight. The Infinity Galaxy shows signs that align closely with DCBH models. Its black hole is already too big, and there's no evidence of supernova explosions or dead stars that would explain it through traditional means. Webb's powerful infrared sensors detect the signatures of heavy gas and gravitational energy, but no stellar remnants. Infinity isn't the only candidate. GNZ11, an extremely distant galaxy previously thought to be the oldest ever discovered, also raised questions about its black hole's age and size. And CEERS 1019, a galaxy just 570 million years after the Big Bang, appears to house another early massive black hole, strengthening the case for direct collapse. Each of these discoveries chips away at doubt. With every ancient light Webb uncovers, the evidence builds. Direct collapse black holes may not be theoretical anymore. They might be the missing link in the cosmic puzzle of how the universe grew so fast, so early. A black hole born in no man's land. While the Infinity Galaxy has captured headlines, another extraordinary discovery adds even more depth to this cosmic mystery. Astronomers using the James Webb Space Telescope have found evidence of a black hole forming in a place where no galaxy should exist, a lonely, starless stretch of space, the vast emptiness between galaxies. It's a cosmic no man's land, and something remarkable is happening there. This black hole wasn't born in the heart of a galaxy, surrounded by billions of stars. It was caught in the aftermath of a violent galactic collision, a merging of cosmic giants that tore matter apart and scattered debris across intergalactic space. Amid this chaos, a black hole emerged, not inherited from either galaxy, but seemingly created by the collision itself. This rare find challenges another core assumption in astrophysics, that black holes only form within galaxies. The data from Webb suggests otherwise. In this unique case, material ripped from the merging galaxies may have coalesced into a dense enough region to trigger a direct collapse, completely separate from any structured stellar environment. There are no stars nearby, no galactic disk, nothing that would traditionally serve as a black hole's cradle. The implications are stunning. If black holes can form outside of galaxies, in the vast emptiness between them, then our understanding of where and how these objects originate needs a major overhaul. It opens the door to the idea of rogue black holes, wandering the cosmos untethered to any one structure, born from the violence of cosmic collisions rather than the quiet death of stars. It also raises new questions about how many of these intergalactic black holes exist, hidden in the darkness. Webb may have only just begun to reveal them. This one, born from chaos, sits as a reminder that the universe doesn't always follow the patterns we expect. Sometimes, even in the emptiest corners of space, gravity finds a way to create something extraordinary. Uncovering the data that's rewriting the universe. To understand just how groundbreaking the Infinity Galaxy is, it helps to compare it to other discoveries that came before it. One of the most notable is CEERS 1019, a galaxy spotted by Webb that existed just 570 million years after the Big Bang. Like Infinity, CEERS 1019 harbors a black hole that appears far too massive for its age. These two galaxies, though separated by time and distance, both point to the same conclusion: black holes form faster and more efficiently than we ever believed possible. The black hole in CEERS 1019 is estimated to be around 9 million solar masses. That's enormous for such an early epoch in cosmic history. Yet the Infinity Galaxy's black hole is even more intriguing. It shows signs of being more massive still, with stronger emission lines and more intense gravitational signatures. The precise mass is still being calculated, but early estimates suggest it could exceed 10 million solar masses, possibly much more. Webb's deep field data has allowed scientists to identify several more candidates for early black holes. In fact, within just the first year of observations, researchers have flagged dozens of potential direct collapse black hole sites scattered across the ancient sky. These aren't random. Many appear in the same kinds of environments: compact, bright galaxies with signs of heavy gas and little evidence of mature stars. What makes the Infinity Galaxy stand out is how complete its story seems to be. Its structure, light spectrum, and surrounding environment match nearly every prediction made by models of direct collapse black holes. There's no stellar debris, no remnants of supernova explosions, and no clear signs of a galactic core packed with dying stars. Instead, there's concentrated gas, intense gravitational heating, and a central object exerting extreme influence, classic indicators of a DCBH. The James Webb Space Telescope's infrared technology is crucial here. Unlike visible light telescopes, Webb can peer through cosmic dust and detect the faintest heat signatures from billions of years ago. It can measure the redshift of ancient galaxies with astonishing precision, revealing not just how far away they are, but how old their light is. This makes it uniquely suited to uncovering early black holes and understanding their growth. Scientists from NASA and the European Space Agency have praised Webb's role in these discoveries. Peer-reviewed studies now suggest that direct collapse black holes may have been common in the early universe, perhaps even the dominant form of black hole formation during the first billion years after the Big Bang. This shifts the paradigm from slow black hole evolution to rapid, large-scale cosmic structuring. The more Webb reveals, the more complex the early universe becomes. What once seemed like a quiet, gradual build-up now looks more like an explosion of formation: galaxies, stars, and black holes all appearing in a tightly packed timeline that's just beginning to make sense. Or perhaps, finally starting to be seen for what it really was. Rethinking the origins of the cosmos, the discovery of the Infinity Galaxy and its enormous early black hole is more than just a fascinating anomaly. It has the potential to rewrite the way we understand galaxy evolution and the structure of the universe itself. Until recently, scientists believed that black holes formed slowly, accumulating mass through star collapse, galactic mergers, and steady accretion. But what if that narrative is only half the truth? Direct collapse black holes offer a radical shortcut to galactic architecture. These behemoths don't just form faster, they create gravitational centers around which galaxies themselves may take shape. This flips the traditional model on its head. Instead of galaxies giving rise to black holes, it may have been black holes that helped give birth to galaxies. The implications stretch beyond black hole formation. One of the biggest puzzles in cosmology has been the so-called missing time problem. Massive black holes were already present when the universe was still in its infancy, and we didn't know how they grew so quickly. DCBHs fill that gap by proposing a mechanism that's fast, efficient, and grounded in the physics of the early universe. It doesn't stop there. These findings could reshape our theories of dark matter as well. The gravitational halos believed to help form direct collapse black holes may provide new insight into how dark matter influences the distribution of mass and energy in the cosmos. DCBHs could act as probes into the invisible skeleton of the universe, helping us trace dark matter structures we've only modeled in simulations. Cosmological models may need to be revised to account for these early giants. Rather than slow, linear development, we could be looking at a universe that built itself quickly and violently, with black holes as the foundation stones. And with Webb uncovering more of these candidates, our concept of cosmic history is rapidly evolving. What once seemed like a quiet, methodical expansion is now beginning to look like a dramatic and complex eruption of matter, energy, and gravitational force. The debate around a cosmic shortcut. Not everyone in the scientific community is convinced that direct collapse black holes are the answer. The evidence is compelling, but critics argue that without direct observational proof, such as gravitational wave signatures or high-precision redshift data, we still can't rule out other explanations for these early massive black holes. Skeptics suggest alternative scenarios. Some believe that dense star clusters could merge rapidly to form big black holes early on, or that accretion rates in the young universe were far higher than current models assume. They argue that, while DCBHs are elegant in theory, they remain hypothetical until we can catch one in the act of formation. The challenge is observational. DCBHs don't emit dramatic supernova light, and they form in environments so distant and dim that even Webb struggles to capture their early stages. But that may change soon. New missions like the Roman Space Telescope and the Laser Interferometer Space Antenna, LISA, are designed to detect gravitational waves and faint signals from deep space. These tools may offer the data we need to confirm or reject the DCBH theory once and for all. Until then, the debate continues, but so does the search. With each deep field image, the James Webb Space Telescope peels back the layers of cosmic time. Now that it's found what may be the first direct collapse black hole, the question becomes, what else is out there? Webb is already scanning deeper into the early universe, exploring regions where galaxies were just beginning to form. These are the cosmic nurseries that could be hiding more DCBH candidates. Astronomers believe Webb may uncover hundreds of such objects in the coming years. Its sensitivity to infrared light allows it to penetrate the oldest, coldest corners of space, places untouched by starlight for over 13 billion years. In these hidden realms, the earliest structures of the universe are waiting to be revealed. If DCBHs are as common as these findings suggest, they could become the cornerstone for understanding early galaxy formation. Webb's ability to analyze chemical signatures, gas distribution, and gravitational effects will help scientists determine how often these black holes formed, what environments they preferred, and how they shaped their surroundings. This research is also essential to mapping the early universe in greater detail. By pinpointing where and when these black holes formed, astronomers can trace the structure of the cosmos itself, like filling in the missing pieces of a giant puzzle. And perhaps the most profound question of all still lingers: what if black holes weren't just a result of galactic evolution, but the architects of the cosmos from the very beginning? If this blew your mind, hit subscribe for more space discoveries. And let us know in the comments, what do you think about direct collapse black holes? Are they the missing link, or just the start of an even deeper mystery?